Okay, in today's video, we're going to be looking at how to differentiate using first principles. And for those of you who've done this before, you would recognize that the formula to work out the derivative of a function using first principles is simply f dash x, i.e. the derivative of f of x, is just equal to f of x plus h minus f of x divided by h. More specifically, we need this function to approach 0. We need x to approach 0, so the calculus way of saying that is the limit as h approaches to 0. Okay, it's the limit as h approaches 0 for what the derivative equals to f dash x. So if we were to continue with this, what we can say is f of x is at the top here. We know f of x is this. So if we want to work out what f dash x is, we first need to work out what f of x plus h is. And we know that f of x plus h simply means changing our input to x plus h. So all I'm going to do is I'm going to take the limit as h approaches 0. And all I'm going to say is f of x plus h is x plus h whole squared plus 5x plus h. And I dot that by just replacing the x with x plus h, replacing the x with x plus h. Now we can minus away f of x. We can minus away x squared and minus away 5x all over h. Now what we can do is we can expand the numerator. On the numerator, we can expand this bracket into x squared plus 2xh plus h squared. We can expand this bracket, the second one, with 5x plus 5h. And then we can do minus x squared minus 5x all over h. Continuing on, what can we cancel from the numerator? We can see that there is x squared and x squared that we can cancel, and we can also see there is 5x and 5x that we can cancel. And if I were to simplify this out, we can see we have the limit as h approaches 0 for 2xh plus h squared plus 5h all over h. And now we have the limit as h approaches 0 for the function. When we cancel out the h's, we can cancel h here, here, and here, and we're left with a h there. We can say that we're left with 2x plus 5. So now what we can do is we can simply let h equal to 0, and you would notice there is no h in here. Right, there's no mathematical violations that are going on here. So all we can say is the limit as h approaches 0 for 2x plus 5 is simply 2x plus 5. And that is the derivative of your function f of x. That is the derivative of this function here. Let's have a look at another question. Let's suppose that f of x is equal to x cubed minus x, and we want to work out the derivative of this function. Find f of x using first principles. When x is equal to 5. So specifically this question is talking about what is the derivative, what is the rate of change of this function here, this cubic, when x is equal to 5. So the first thing we do is we need to first differentiate by first principles. And we know, back to the formula, f of x, f dash x, is equal to the limit as h approaches 0 for f of x plus h minus f of x all over h. And so we're going to do this process with this equation here at the top. So all we have here is the limit as h approaches 0 for f of x plus h is simply replacing the input x with x plus h. So x plus h whole cubed minus x plus h. And then we can minus away f of x. So if we minus away f of x, which is literally this function here, we can minus away x cubed, and we can add back x. And the reason we're adding it back is because a negative and a negative make a positive. So continuing on from here, we can divide all of this by h. Now we would expand out the numerator. So to expand out the numerator, we get the limit as h approaches 0 for x cubed plus 3x squared h plus 3xh squared plus h cubed. And if you're wondering how I did this in my head, there is a nice technique using Pascal's triangle, how you can expand this out. I'll do that in a separate class or separate video. But in this case, manually expand this out, expand this how you wish. This is the expansion of this brackets. Minus x take h, me expanding the minus here, minus x cubed plus x, all over h. Now what we can do is we can simplify out the numerator. We can simplify the numerator by basically cancelling out the x cubed terms, cancelling out the x terms, and that's all we can cancel out here. So what we're left with is the limit as h approaches 0. It's a hassle to write this every single time, but every single line you do, you must write limit as h approaches 0, as annoying as it is. So h plus 3xh squared plus h cubed minus h all over h. So now what we can do is we can simply start cancelling out the h terms. We can cancel out a h here and here. Here we can cancel it out to get left with h. Here we can cancel it out to get h squared. And here we can cancel it out to get 1. So continuing here, all we're left with is the limit as h approaches 0 for 3x squared plus 3xh plus h squared minus 1. And if you notice, there's nothing we're violating here. There's no mathematical nonsense that we end up with, such as divide by 0. We're allowed to make h equal to 0 now. And if we make h equal to 0, the equation that we're left with is 3x squared plus 3xh will just cancel out. So this term cancels, then this term cancels when we make h equal to 0. And we're left with 3x squared take 1. That is the derivative. That is what f dash x equals to. But the question specifically asked us for when x equals to 5. So more specifically, they're asking us, what is f dash x when x equals 5? What is f dash 5? So we have f dash x over here. We just worked out this equation. So to work out f of 5, f dash of 5, all we have to do is 3 times 5 whole squared minus 1. And that becomes 75 minus 1, which equals to 74. That is the rate of change for this cubic when x equals to 5. Alright, the next example we're going to look at is when f of x is equal to 3x times 2x take 4. And we're just simply going to work out what is f dash x. Okay, we're going to work it out using first principles. And again, the formula to work out this is the limit as h approaches 0 for f of x plus h minus f of x all over h over here. I have a little speech impediment there, my bad. Now continuing on, what is f of x and f of x plus h? Whenever we do first principles, it's much easier if you work with the expanded form. So I'm just simply going to expand this out, and I'm going to say it's 6x squared minus 12x. That is the fully expanded form. So now we're going to do first principles, differentiation by first principles, with that equation instead. So what we're going to do is the limit as h approaches 0 for 6x plus h whole squared minus 12x plus h minus 6x squared plus 12x all over h. Again, we can expand out the numerating terms. So limit as h approaches 0, 6 times x squared plus 2xh plus h squared minus 12x take 12h minus 6x squared plus 12x. And I couldn't do this in my head, so we're just going to simply expand out the 6 to each of these terms over here. So doing that, we get 6x squared plus 12x plus 6h squared. Like this. all over h. Now we can continue. What I can see is we can cancel out the following terms. We can cancel out 6x squared. We can cancel out 12x. And that's all I can see so far. So we can do the limit as h approaches 0 for 12xh plus 6h squared minus 12h all over h. And we still can't sub in 0 for h because of the fact that we'll get divided by 0. So that's why we want to do cancelling out of the h. We can cancel out h here and here and here. We can also cancel it out here, but we need to have another h left over. So now what do we have left? We have the limit as h approaches 0 for 12x take 12. And we can notice there is no h in here, so the limit as h approaches 0 is simply the inside function. That is the derivative f dash x. This is what f dash of x is equal to. We'll do one more example for this video. And the last example in this video that we're going to do, we're going to make it a little bit more tricky. We're going to be doing y equals to x to the power of 4 take 2x squared. We're going to be differentiating this using first principles. So what is the derivative dy over dx? You can pause the video and have a go at this last one by yourself. Okay, that's enough time. The derivative dy on dx is simply equal to the limit as h approaches 0 for f of x plus h minus f of x all over, you guessed it, h. Now in doing so, we don't have a function anymore in terms of x. We don't have f of x equals to something. We have y. We can treat y the same way we do f of x. So f of x plus h is simply replacing your input, and your input in this case is always x. We can replace our input with x plus h. And in doing so, we will have the limit as h approaches 0. Instead of x to the power of 4, we can say x plus h to the power of 4. Instead of saying minus 2x squared, we can say minus 2x plus h whole squared. Then we can minus away the original function. In this case, we're treating this as f of x. So as we keep going, we can minus away x to the power of 4. We can add 2x to the power of 2. All over h. And again, the hard and tedious part of doing all this is simply doing the expanding. We have to expand all of the numerator at the top here. So the limit as h approaches 0 for x plus h to the power of 4. You can simplify this using whatever way you want, whatever technique. I like doing the Pascal triangle method. So this would be x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the power of 4. Minus away, expanding this bracket out, we're left with 2x squared plus 4xh minus 4h squared. And if any part of this you want fully explained, be sure to comment at the bottom and I'll get back to you if you're unsure of how I expanded anything in this video. Divided by h. Yuck, what a disgusting equation we have here. So what can we cancel? That's the first thing I want to look at. I can see that we can cancel out an x to the power of 4. I can also see the 2x to the power of 2. And that is about the only thing that I can see in this entire equation. Absolutely fantastic. So what we're left with is the limit as h approaches 0 for 4x cubed h plus 6x squared h squared plus this plus h to the power of 4 plus 4xh take 4h squared. And all of this is divided by h. What can we cancel with h? Pretty much every term here we can cancel with h. We can see that the h cancels with the h here and the h here. It cancels with the h squared to give us h, cancels with the h squared to give us h, cancels with the h cubed to give us h squared, and cancels with the h to the power of 4 to give us h cubed. So what we actually have left as our final equation is the limit as h approaches 0 for 4x cubed plus 6x squared h plus 4xh squared plus h cubed plus 4x take h. And if you notice here, all I see is the limit as h approaches 0. I see no divide by 0 scenario going on. So what we can literally do is sub in 0 for h. For each of these terms, we can sub in h equals to 0. And in doing so, this term will cancel out, so will this term, so will this term, and so will the last term, because 0 times anything is simply 0. So that would mean we have the limit as h approaches 0 for 4x cubed plus 4x. And wow, there's no h's left. So that means the limit as h approaches 0 is the inside function, because there's no h involved. So that means that the derivative dy over dx, in this case, is simply 4x cubed plus 4x. And that is how you do integration, and that is how you do differentiation by first principles.